Imagine for a moment, you are one of our earliest ancestors. You huddle around a crackling fire. The day's hunt is now a nourishing meal. The sun has long since dipped below the horizon. Night plunges into deep, primal darkness. But you are not entirely without light. High above, a brilliant silver disk hangs in the velvet sky. It casts a soft, ethereal glow upon the landscape. It is your only nightlight in a world of unseen dangers. This companion is a constant presence. It changes its shape in a predictable, comforting rhythm. It waxes from a sliver. It grows to a full, glorious circle. It then wanes back to nothing, and is reborn again. The moon didn't just illuminate the darkness, it ignited human curiosity. It was the first astronomical object people truly watched. Its phases became our first calendar, a way to track time, to know when to plant and when to harvest. Its gravitational pull governed the tides, a mysterious force that shaped coastal life. Our ancestors saw faces, rabbits, all manner of figures, and wove stories of divine powers and deep significance. When Neil Armstrong uttered those immortal words, "That's one small step for a man, one giant leap for mankind," it felt like we had finally conquered the moon. On July 20th, 1969, humanity achieved what was once pure fantasy. We bridged the quarter-thousand-mile gap and planted our feet on another world. The Apollo missions were a triumph of science, engineering, and sheer human will. Astronauts walked on the lunar surface, collected rocks, and conducted experiments. They gave us a perspective of our own planet, the pale blue dot, that forever changed our consciousness. We brought back nearly 400 kilograms of lunar material, a treasure trove for science. For a brief, shining moment, it seemed all the moon's secrets were about to be laid bare. We had the samples, the photographs, and the first-hand accounts. We learned of its fine, powdery regolith, its lack of substantial atmosphere, and extreme temperature swings. Data helped piece together the giant impact hypothesis, that a Mars-sized object struck young Earth, birthing the moon. It felt like a final chapter, but exploration often creates more questions than it answers. Apollo visited only a handful of near-equatorial sites on the near side. Like visiting 6 small towns and claiming you know the whole planet. Most of the moon, larger than Africa, remains untraveled. Our samples are invaluable yet limited, leaving a biased, incomplete picture. The moon isn't a solved puzzle. Its deepest secrets endure. One enduring puzzle lies within the rocks Apollo brought back. We expected mantle material blasted into space, but computer models suggest the moon should be mostly from the impactor, Theia. So why do moon rocks look so much like Earth? It's a glaring contradiction. Then there's the enigma of the far side, not truly dark, but very different. Near side, vast, smooth, dark plains of volcanic basalt, the Maria. Far side, rugged, heavily cratered highlands with a thicker crust. Why this stark dichotomy? Residual heat from a molten Earth may have kept the near side thin and volcanic, but we need more exploration to prove it. Perhaps the most poetic mystery is the moon's slow, graceful departure. It drifts about 1.5 inches, 3.8 centimeters, away each year. Tides raise ocean bulges. Earth's rotation drags them ahead, tugging the moon forward into a higher orbit. We measure this with lasers bounced off Apollo reflectors. Rewind time and the moon loomed large. Tides were colossal, days shorter, shaping conditions for life's evolution. Understanding this orbital history reframes our past and future. The moon has actively shaped Earth. Its slow goodbye reminds us the solar system is always changing. For decades, the moon was considered the driest place, a magnificent desolation. Apollo samples were bone dry, reinforcing that water would vaporize under solar wind and sunlight in vacuum. Our perspective began to shift. Clementine and Lunar Prospector hinted at hydrogen concentrated at the poles. Tantalizing, not conclusive. In 2009, NASA's L-Cross crashed into a shadowed crater near the South Pole. The plume revealed significant water vapor and ice, a game-changer. Lunar Reconnaissance Orbiter and Chandrayaan-1 confirmed water isn't confined to a few craters, it's more widespread. Ice lurks in craters unlit for billions of years, and water molecules may be trapped within the lunar soil across the surface. This discovery rewrites our exploration strategy. Water is essential for life and growing food, split into hydrogen and oxygen, the primary components of rocket fuel. The moon could become a cosmic refueling station, enabling missions to Mars and beyond. Could icy craters preserve ancient organics or dormant microbes delivered by asteroids, or even from early Earth? It's a long shot, but a discovery there would reshape our understanding of life in the universe. Exploring the moon is not a walk in the park. It is one of humanity's most formidable challenges. There's no substantial atmosphere, no air to breathe, no pressure to stabilize liquids, no shield from radiation or micrometeoroids. Survival demands heavy shielding and robust systems. A tiny pebble that burns up on Earth could be lethal on the moon. Lunar dust isn't beach sand. It's sharp, jagged rock and glass forged by billions of micro-impacts. It's abrasive and electrostatic, clinging to everything. Overheating gear, scratching helmets, even irritating lungs inside the module. Managing dust is a massive engineering and health challenge. With no air to buffer heat, temperatures swing from searing days to 2-week nights far below freezing. Equipment must be rugged, power systems survive the cold, habitats stay livable, batteries kept warm, materials resist brittleness. Reaching the moon is hard and expensive. Every pound demands immense fuel, and rockets, landers, rovers, and habitats take years and billions to build. Unlike Apollo's rush, today requires sustained will and global collaboration. The moon is near, but it does not give up its secrets easily. Radiation, dust, temperature, and cost explain why we haven't returned to stay yet. As we stand in late 2025, we are on the cusp of a new golden age of lunar exploration. The silence is about to be broken by the hum of rovers and the crunch of boots. The Artemis program, with global partners, aims to land the first woman and the first person of color on the moon and build a sustained presence. This isn't about flags and footsteps. It's about a permanent outpost and a stepping stone to Mars. A small space station, Gateway, will serve as command center, lab, and waypoint to enable frequent, complex missions. Robots will map resources and test tech, while commercial landers under CLPS drive innovation and reduce costs. Rovers like Viper will survey the South Pole's permanent shadows. They'll map water ice, the first resource map of another world, guiding Artemis base camp sites. Seismometers will probe the moon's interior and why the far side differs so much from the near side. China, Russia, India, Japan, and Europe advance ambitious programs. China's Chang'e landed on the far side, revealing a realm once hidden. Competition and collaboration together accelerate discovery. The coming decade promises a flood of data that will challenge our theories. The moon is about to get very busy. So, why does any of this matter? Why invest so much to study a seemingly dead rock? The moon is not just a rock. It is a time capsule, a scientific laboratory, a mirror reflecting our past and future. Without atmosphere or plate tectonics, its surface preserves a 4.5 billion year record of cosmic events. Its craters chronicle the bombardment both our worlds endured, a history erased on Earth by erosion and geology. Meeting lunar challenges drives innovation, sustaining life in vacuum, powering through 2-week nights, recycling water and air. These advances ripple into medicine, renewable energy, water purification, and materials science. Computing leaps from Apollo helped spark the digital age. Tomorrow's lunar tech can help us live more sustainably on Earth. A living outpost on the moon expands our sense of the possible and inspires young minds towards science, technology, engineering, and mathematics. It unites people in a peaceful, shared endeavor, reminding us what we can accomplish together. What secrets lie in its icy shadows and ancient craters? Could it harbor evidence of life's building blocks? Can the moon become our stepping stone to Mars and the stars beyond? These answers are about us, our origins, our capabilities, and our destiny. The moon is part of our world, inextricably linked to our past and future. By exploring it, we explore ourselves.